We're going to conclude by taking a look at the binomial probability models, but with respect to the normal distribution. We've done a lot with the normal distribution, so we won't focus too much on actually doing the normal. We'll take a look at this situation. So before we get into all this notes, let's think about this situation. So we used donating blood and finding an O negative as an example. So suppose that the chance of someone donating O negative blood is 6%, and you've got 32,000 donors, and you want 1,900 of them to have O negative. So if we take a look at our distribution setup, or our probability setup, we would have to type this into our calculator. 32,000, choose 1,900, times 0.06 to the 1,900, times 0.94 to the 30,100. And that is simply beyond our calculator's ability to calculate, or at least beyond its ability to calculate it accurately. So we need to be able to do something else. And that gets us into the situation where sometimes our sample size and the number of successes is too small or too big for us to just use the calculator and type in this formula. So if our number of successes, that is, if our mean NP, if that's greater than or equal to 10, so we have a number of successes greater than or equal to 10, and if we were to do NQ, find the number of failures, if that's also greater than or equal to 10, then we can use the normal distribution instead of this formula. So, the normal approximation with samples, with large samples, the normal distribution can give us an approximation for the binomial probabilities. But, like I was saying, we have to have at least 10 successes and 10 failures to use this normal approximation. That means NP has to be greater than or equal to, and NQ has to be greater than or equal to 10. But an important difference is this. The binomial probability is discrete, meaning we find only like a couple numbers. So in our examples, like we found the number of successes, say 2 successes or 3 successes. In this case, in our example, we wanted exactly 1,900 successes, but the normal distribution is continuous. And that means that we can't find this 1,900 exactly, but using the normal distribution, we can do a range. So if you remember, our normal distribution looks something like this roughly. And what we're saying is our mean is right here in the middle, and we could find a range. So I don't know where this 1,900 lands here exactly, but let's say that it is over here. So if it is over there, then what we would find is maybe this in our example with the donation. Like, I'm sure that with O negative being a universal donation, that the Red Cross or whoever's doing this collecting of donors wouldn't mind getting more than 1,900. They don't need to get 1,900 exactly. So we would find this right tail end area under our curve. Okay, so normal approximation. First, we're going to identify that we do indeed have a binomial situation. And then we're going to use these formulas right here to get our mean and standard deviation. And then we'll use our calculator's normal distribution to get our answer. So let's go ahead and take a look at our example. So here's the example that we started with. This 3,200 people are giving blood, and what's the chance that a person has, or the chance a person has O negative is 6%. What's the chance that at least 19 people, so notice we can't do exactly 1,900 people, but we could do at least. So our mean is going to be NP. So that's going to be our number of trials is 3,200, and our chance of success is 0.06, so 6%. And when I type that into our calculator, or my calculator, I get 1920. All right, so this is actually a very good chance that this is going to work out. So our standard deviation is going to be square root of NPQ. So I'm going to multiply that previous answer by 0.94 because our Q is going to be 0.94. So our standard deviation is 18. Oh, well, I have to square root that. So square root that, and I get our standard deviation is 42. So I go into my calculator, and well, I guess that was there the whole time. So I went into my distribution. This would be your stat distribution that we want to get into. I'm going to go to distribution. I'm going to go to normal and norm CD, normal CDF. Our data will be variable. Our lower, so we want at least 1900, and we want to go up to, well, infinity, so I'll put 10 to the 10th in there. And our standard deviation was 42, and our mean is 1920. Okay, and we'll go ahead and execute that, and we get a 68% chance that we get enough. So what about of less than 1,000 people? So our mean and our standard deviation doesn't change, but the way that we would put this into our calculator does. So I'm going to keep the mean and standard deviation the same, but this time my upper end, I want less than 1,000 people, so that means no more than 1,000. And my lower is going to be negative 10 to the 10th. I want to get every possibility in there. And we'll execute that. And, the chance of that happening apparently is 0. Let's just double check that I put that in right. Maybe that makes sense. Yeah, that actually does make sense. So let's say that instead of this being 1,000, let's say of less than 1,800. That probably would have been a better number right there. So let's try that. I'll show my calculator again. So let's go an upper of 1,800. That's a little bit more reasonable given our standard deviation. And there we go. So 2.1 times 10 to the negative third. That's what that E would mean if your calculator pops an E. So move that 3 spots and then change to a percent, and we get 0.21% chance that happens. The chance of a wreck on a certain highway is 1%. Each week, 50,000 cars go through the highway. Can the situation be modeled with a normal distribution? So remember, our mean is going to have to be greater than or equal to 10. And so our number of successes and our number of failures will actually have to be greater than or equal to 10. So NP and NQ has to be greater than 10. So if I do NP, that's going to be 0.01 times 50,000. And that has to be greater than or equal to 10. Let's see if it is. Type it in. I'm pretty certain it is. Yep, that's 500. So that checks out. And then 99 times 50,000. Well, that's definitely greater than 10. But just to put it in, that is 49500. So yeah, that's greater than 10. So whenever we do have these large numbers, we're pretty much safe. So what's the chance of more than 800 cars having a wreck? So I need my mu. My mu is 500. My standard deviation is going to be the square root NPQ. So that's going to be square root 500 times Q is 0.99. So my standard deviation is 22.2. So we'll put in all that information. Exit this out. So we're going to change this. So we want more than 800 cars. So 800 is the lower bound right here. And our upper bound is going to be 10 to the 10th. And our standard deviation, 22 point, oh, where's my decimal point? 0.2. And our mean, 500. We'll execute that. So very small. Yep, because boy, I chose really bad numbers here. So let's say more than, change this number. Let's say more than, let's do more than 600 cars. That'll be better, hopefully. So our mean, oh, I didn't want to clear out that. Oh boy, I'm really messing everything up. Oh, I turned off my pen, that's why. I'll turn my pen back on. So our mean still is 500. Our standard deviation still is 22.2. But now, oh, I'm doing cows. Oh, there it is. Okay. So this one. So I'm just changing that number to 600 so that it actually works out. So I want lower to be 600. So we want more than 600 cars to have a wreck. Okay, that's getting us a little bit more reasonable there. So 3.3 times 10 to the negative 6. So that would be this. 1, 2, 3, 4, 5, 6. Yep. So as a decimal, we're looking at moving this twice. So a very small chance that we would have more than 600 cars. I'm just kind of curious now how many till we get to like a very reasonable number. So let's try more than 580 cars. Let's try 580. See what happens. So all this stays the same. So upper, still 10 to the 10th. So up here, 580. So when we think about that, if our standard deviation is 22, that's going to be about 4 standard deviations out. So it should be a very small number. And it is still, but we're getting closer to a reasonable percentage. Okay, one more slide, the cow situation, so we'll ignore that right there. There are 18 cows in the field. The chance of a cow being infected with some sort of disease is 30%. can the situation be modeled with a normal distribution? So our NP has to be greater than or equal to 10, and our NQ has to be greater than or equal to 10. And in the case of our NQ, that would be 18 times 0.7, and that is actually fine. So no worries there, I get 12. But when I do NQ, 18 times 0.3, I get 5.4. So can it be modeled normally? No. All right, so then how do we answer this? The chance of 3 or less cows. So that would be 3 cows, 2 cows, 1 cow, no cows. So I'll just start setting it up, but I won't finish it. So we have to do it this way. 18, choose 3, times, we're just using this formula, NCR, P to the R, Q to the N minus R. So this is going to be 0.3 to the 3 and 0.7 to the 15th. And then we add to that 18, choose 2, times 0.3 squared, 0.7 to the 16, plus 18, choose 1, times 0.3 to the 1, 0.7 to the 17, and finally 18, choose 0, 0.3 to the 0, 0.7 to the 18. If we typed all that in, that would get it to us, or we could type them all individually in and add them all up in the end. Okay, this wraps up our section on the binomial probability and approximating it with the normal distribution. Too bad all my numbers were screwy, but that's okay. Same idea.